Welcome to the course on computer design of electrical machines. We will have a lecture 34 today on the design of stepper machines, part 1. With the outline of the presentation, we will start from introduction, then application of stepper machine, then we'll go for construction, classification, operating principle of stepper machine, then converters for stepper machine, then macro stopping control of stepper machine, then exercise, numerical problems and references. Well, to start with, you can just see how the stepper motor look like of different variety. From the internal construction, like as well as the total body from the outside, So now you can just see a stepper motor is a special electrical machine which rotates in discrete step in response to program sequence of input electrical pulses. It is also known as a step motor or stepping motor or stepper motor. It's known from typically will all three names and you can see how the photograph look like of a stator winding. So we have a winding on the stator, and on the rotor we have only the either the salient pole structure or the permanganate, or along with the permanganate we have a typically the salient or teeth structure So now you can just see how the typically incremental motion is there. On the animation you can see a stepper motor is an electromagnetic incremental actuator which converts digital pulse input to the analog output motion, shaft motion, and the shaft of the stepper motor rotates in equal increment in response to a chain of input pulses. When properly controlled, the output steps of stepper motor are always equal in number to the number of input pulses. So now coming to stepper motor that moves in one step at a time. So a digital version of the electric motor, and each step is defined by a step angle. As you can see the step angle how it is defined for, typically for start position, then step 1 and 2 Now coming to the advantages of stepper motors. Stepper motor is generally a discrete motion device. Therefore, it is more compatible with modern digital control techniques, and it is more easily adaptable for interfacing with the other digital components. And the position error in stepper motor is non-cumulative. It is possible to achieve accurate position and speed control with a step motor in an open loop system, and thus avoiding the ordinary instability problem and elimination of feedback transduction. Then power consumption for intermittent operation is reduced during quiescent periods for a permanganate type of stepper motor, and design procedure is simple for step motor control system. Is low cost for control is achieved, and high torque at start and low speed, ruggedness, simplicity of construction, can operate in an open loop control system, low maintenance, typically high reliability. Then the rotation angle of the motor is proportional to the input pulse, and the motor has full torque at standstill if windings are energized. Then the precise positioning and repeatability of movement, since good stepper motors have an accuracy of 3 to 5% of step, and this error is non-cumulative from one step to the next. An excellent response to starting, stopping and reversing. Now coming to the applications of stepper motors, you can just see how different sizes and shape stepper motors are there in the typically of different ratings in the photograph, from a very small to reasonably large size stepper motor which give a very large torque for many applications And the typical application, you can think about the industrial robots, in which for different degree of motions are used, and linear actuators. Your rotary motion is converted to linear motion with the help of this kind of arrangement for number of applications. Then rotary actuator, then typically the goniometer for precise angle measuring device, and then telescope angle control. Then the gas valve with the stepper motor, then stepper motor in the disk drive, then stepper motor in printers, then stepper motor in security cameras, then in stepper motors in slot machines, then typically application in antenna pointing system, then your numerical control machine, CNC machines, for the typically for all three axes the three motors are used for X, Y, Z. Then the 3D printers, as you can see in the animation photograph, how really the stepper motors are used for the providing the different kind of the actions in 3D printer. Then typically the hybrid motor 1.8 degree stepping motor of size is of 34, means 3.4 inch diameter and 27 to 37 typically. Then the stepper motor in floppy disk type. Then flatbed scanners. For all the motion we use the stepping motor. Then the computer printers. Then the plotters. Then the image scanner. Then the camera lenses. Then the CNC machines. Then the solar panel tracking for maximum power tracking for mechanical motion. Then the fax machines, surgical robots for providing all the motions. Then the infusion pumps. Then the medical field for CT scanner. Now coming to this is, I think, some of the applications. There are many more practical applications if you divide into different applications. Now construction and classification of stepper motor. Of course, so stepper motor construction and classification. Stepper motor consists of a palm magnet sandwich between the two rotor half, causing axial polarity, which make up the spinning part of the motor, placed into stator housing where the stator coils of wire make up the different motor phases. A bipolar stepper motor, also known as two-phase hybrid stepper motor, and each phase has a 4 coils, as you can see typically in the photograph. The rotor is connected to the motor shaft. The bearings on the either side of the rotor allow for smooth rotation with little friction and wearing, and the bearings are placed into their designated spaces in front of and rear end caps, which allow for the concentricity of the rotor inside the stator, and perfect alignment of the rotor and stator is quite important. Now you can just see how the different parts, exploded view of a stepper motor of the different parts, starting from front end ball, then ball bearing, then rotor shaft, rotor laminations, then magnet, then rotor laminations, typically the winding insulation, then your ball bearing, then stator laminations, winding insulation, then spring washer, and rear end ball with the screw. So these are kind of a different components of this stepper motor. You can see more than 10 components of this small stepper motor, and then stator assembly. I mean, you just have all these parts into that. Now you can say this classification for stepper motor is starting from palm magnet. Then in variable reluctance we have a two kind, single stack, multi stack, and then we have a hybrid. So you can see multi variable step reluctance step motor is a typically kind of a refined, form of the reluctance motor, because we have a silencer on stator and rotor. There is no permanent material either on rotor. Only in stator we have the winding. With, of course, to reduce the step angle, we have a number of teeth or poles on the rotor quite high in number. Then we have permanent. Permanents are only put on the rotor, and the winding is put on the stator. Of course, in variable reluctance type stepper motor, we must have more than 3 phases for the bidirectional rotation. But in permanent motors and hybrid motor, which have a permanent as well as slotted structure of the rotor, we must have a typically we can have even 2 phase also, and we prefer to use 2 phase in permanent stepper motor hybrid motor. And but we need a converter which you can call it have a bidirectional current to make a both N and S pole from the stator side, because poles of rotor are already fixed. But in case of variable reluctance motor, typically more than 3 phases are required. So now coming to variable reluctance step motor, the first category. As you can see in the photograph, we have a silencer on stator and rotor. So variable reluctance motors, the construction of variable reluctance motors is generally shown as shown in the figure. There is a stator assembly consisting of insulated laminations stacked with copper coils wound around the teeth. The stator assembly is positioned within a housing or main frame so that its location is secure. Then the rotor assembly consists of a steel magnetic core and a steel output shaft and bearing, and the rotor assembly is centrally located inside the stator assembly by end frames or bearing supports. Now coming to its operation. So when stator phase is energized, the soft iron rotor is electromagnetically attracted to the stator pole, and rotor tooth attempts to line up with a nearest energized stator pole. A magnetic flux path exists from the stator pole to rotor teeth through the rotor to different rotor tooth, and stator pole and around the stator back iron. So when the rotor teeth are directly lined up with the stator poles, the rotor is in a position of minimum reluctance to the magnetic flux. If external torque is applied to the rotor, a counteracting torque is developed, which tends to restore the rotor to a position of minimum reluctance or maximum inductance. So a rotor step takes place when one stator phase is de-energized and the next phase in sequence is energized, thus creating a new position of minimum reluctance for the rotor. Now the typical example, as you can see how it is really the winding of a one phase on the two pole of variable clamp motor, and how really typically you can go with the different positions like also. Now this is another typical example. If you change the excitation from 1 to 3 phase, how the rotor continuously rotate if you really giving a pulses at the fast rate. But if you give very slow rate, then it move only in incremental motion. So this is usually a 4 wire motor. The common wire goes to the positive terminal of the supply voltage of and the rotor has 4 poles and the stator has 6 poles. It is a 30-degree step angle motor like so that how it is really step angle is there. Number of 360 by number of poles, that become 90, and in 90 degree all the three phases should be excited. So 90 divided by 3, it becomes 30 degree, which is a step angle, and we call it stock angle like. So now this way the variable reluctance step motor to rotate, we excite the three phase winding in a sequence that is given here. W1, W2, W3, all the three phase winding in a sequence is starting from 1, then 0, 1, then 0, 0, 1, and this gives the full 2 rotation as these numbers, of excitation of different switches, or you can call it the transistor in three phase are there. Like, why we have a positive supply with the common terminal? Because we can connect the common base drive or gate drive of the MOSFET or base drive of transistor, we can connect to a common ground, and which really simplified the gate drive of these, or you can call it the diverse circuit like, and cost also it's reduced. So now it has no operation of variable reluctance motor. It has no permanent or either on rotor or stator. The rotor carries no windings and has shell and pole construction, and the rotor and stator both are made of soft iron stamping. The stator also have a shell and pole and carry the stator winding, and number of stator pole is an even multiple of the number of usually of the phases which for which the stator winding are wound. So number of phases must be at least 3 for bidirectional control of stepper motor. It can have a single stack or multi-stack construction. So torque developed by a motor shall be more in case of multi-stack motor. So here first case is the 6x4 3-phase stepper motor. Another second case is the 8x6 4-phase stepper motor. With the first one is the 30-degree step angle and second is 15-degree step angle. Now the magnetic flux seeks a lowest reluctance path. So magnetic circuit and stator coils energized in the group called phases. And as you can see, the for the motor of 8x6 4-phase stepper motor, the excitation sequence A, B, C, D, or you want to reverse the rotation, that's A, D, C, B, A or so. Now this variable reluctance motor is normally we call it also unipolar motor. So here typically you can call it 2 coils, each with a center tape, and the center tape is connected to positive supply, and end of which are alternately grounded through the, let's say, to the solid state switch like maybe transistor or MOSFET, and of course have a typically low torque in the of this like, and this the way of how you are exciting the winding pole. This gives the 2 full rotation with the such excitation, and then the basic actual waveform for this 4-phase kind of a stepper motor like. So now coming to this bipolar, you say with the palm magnet, usually we must have a bipolar excitation. So here 2 coils, no center tape, and able to reverse the polarity of current across the coil and higher torque per than the unipolar excitation. The typically bipolar excitation, as you can see here, is a H bridge here. So it's a typically more complex control and driver circuit. Coils are connected to H bridge circuit, and voltage applied across the load is in either direction, and H bridge requires for each coil. Now coming to the operation of this, the step angle. It is the angle through which an unloaded stepper motor rotates for every step for an Z sequence. That's a theta is equal to 360 by Z, where the Z is steps per revolution. It is given by Z equal to 360 by theta s, and the step angle theta s is governed by the following relations: Ns equal to your MP or equal to NR plus minus P, where NS and R the number of stator and teeth of the stator and rotor, and P the number of teeth per phase, minimum 2. So here the Z becomes equal to 1 upon, in bracket, absolute value of 1 upon R to minus 1 upon S, or NS S NR minus divided by NS minus NR, absolute of that. So because this Z should be always positive number, so an integer, so that's the reason we take absolute. So from this Z we get PM M minus 1 for NS greater than N, and equal to PM in bracket M plus 1 for NS less than NR, where N is the number of phases. Now coming to the permanent rotor type of stepper motor, as you can see permanent on the rotor and the winding on the stator. These motors can be also two phase as is shown. We pivot to two phase because the driver circuit, basically power converter circuit, also become cost effective with the two phase motor. Here we can get a bidirectional features even with the two phase because of the magnets on the rotor, and we have to change the polarity of the current in the your stator winding because of to make a the pole opposite pole from the rotor, and which require directional features of the winding current. Like so, this permanent rotor step motor, it consists of two sets of stamped steel cup with the diagonal teeth facing the rotor, and each set of cups circums a coil of the wire, and the two sets are positioned with respect to each other such that they circumrime the rotor, but they are offset from each other by 1/2 of a tooth pitch. Then it's sometimes called a simple PM step motor, but should not be confused with the hybrid permanent step motor. The rotor is a stamped construction motor in a smooth cylinder magnet permanent radially magnetized with the alternating N and S pole, as you can see in the typically in the figure. So the stator have a two cup shape half with the form stator teeth, as see in the figure, and each half contains a circular bobbin wound coil. Because of this simple design, the price is low, but step accuracy and speed may not be equal to the performance of the other step motor type. And two types of winding connections, bipolar, or we call it monofiller, single winding per bobbin, or unipolar called bifiller, and two winding per bobbin. So it has a permanent on the rotor and also known as can stack motor, and due to its low manufacturing cost, it is employed in a paper feed motor of printers for head drive or of a floppy disk drive. Then this typically you can see the photograph and different parts of the motors starting from typically retailing ring, then washer, then phase A coil, outer stator, then inner stator, then housing, then rotor of permanent, and then shaft. Then you have a phase B coils, front cover, and then sintered sine wave bearing and weather protection, as well as the PCB4 control. So the individual stator halves have uniformly spaced teeth, and the two halves are offset by 1/2 of the tooth pitch. The rotor contains the same number of teeth as each of stator half, and when one stator half is energized, the rotor aligns its pole with the stator teeth of opposite polarity. A flux path exists from stator tooth to opposite rotor pole, between adjacent rotor pole, back to the opposite adjacent stator teeth, and through the stator back iron. When the energization is switched from one stator half to the rotor move in a new position of alignment 1/4 of a pole pitch from the previous position, and the next step occurs when the original stator half is energized with the opposite polarity. A 4-step switching sequence produces a movement of one pole pitch, and the same motion may be achieved by energizing both stator half at once and allowing the rotor to align itself with the resultant magnetic field. A typical motor of this type have either 12 or 24 poles per stator half, and thus produce a step angle of 15 degree or 7.5 degree respectively. Now the rotor has permanent. The teeth on the rotor and stator are offset, and number of teeth determine step angle, and holding a residual torque are produced in this case. You can see at the different stage 1, 2, 3, 4 with the purple color for energization, and you can just see the different. You can see like how it is with the four 4-lead bipolar, then 8-lead unipolar excitation with the midpoint of the winding, and the different kind of configuration for connecting the typically the winding and the two edge bridges for two-phase to have a current control independently, or you have a unipolar excitation where the midpoint is used to the supply and the transistors are connected to the lower point, so that the gate drive is common and cost of the typically of you can call it power electronics or the driver circuit is low. But the disadvantage at a time half the winding is used. In comparison to get higher torque, we use the bipolar winding where two edge bridges are used for exciting of the two separate phases windings. And you can just see how the typically with the excitation of the magnets, really are attracted, and you get the motion typically of this PM stepper motor. Now coming to third category of hybrid permanent stepper motor, these are typically called the hybrid because of the two nature. We have a saliency as well as the permanent. That is one way. Another is of course we have a axial field as well as radial field in these motors. So hybrid step motor have a stator assembly similar to that of VR stepper motor, but the rotor consists of three sections. So two pieces are similar to variable reluctance motor rotor, but a magnet is placed between them and they are offset circumferentially from each other by one half of the toothpiece. This motor termed as a hybrid because its used is elements of both variable reluctance and permanent rotor step motor, and the commonly known version is a 1.8 degree step angle motor. This is quite popular, and it was originally designed as AC2 type synchronous induction motor for low speed application. Now the stator construction is similar to that of variable reluctance type motor with a salient pole, multiple teeth per pole, and the phase windings may be either monopolar or bipolar coils I discussed for the stem construction motor. The rotor contains a cylindrical permanent axially magnetized and enclosed on the each end by a soft iron cup with the uniformly spaced teeth. And as for the variable reluctance motor, the number of stator phases and the differing number of stator and rotor teeth determine the step angle. And you can just see how typically the photograph of different parts of here. You have a winding, then you have a stator slotted structure, then you have a two permanent rotor with the two south rotor cup and north rotor cup, and magnets are parallel to the shaft. Which really, so you can call it in these structure from the by stator to rotor. You have a what you can call it field is or flux move your radially, and then in the rotor in magnet it's move axially, like as you can see by exciting how it is really moving. By excitation, by incremental motion from the rotor side, you have a saliency as well as permanent on the rotor. So you have many motors of different sizes of this kind. So you can see on the rotor in the photograph that you have even permanent as well as you have a saliency, and you have a different parts including the typically for this hybrid stepper motor and a couple of stacks with the different parts of open form like. So now coming to like a can stack kind of PM stepping motor, can stack construction results in a relatively large step angle, but its overall simplicity ensures economic high volume production at very low cost. And the drawback includes resonance effect and relatively long setting time, rough performance at low speed unless a micro stepping drive is used, and liability to undetected position loss as a result of operating in open loop. And the current of the motor is practically independent of the load condition, and the winding losses at full speed are relatively high and can cause excessive heating. At high speed, the motor can be noisy. So here is the specification of can stack stepper motor manufactured by Thomson Air Pax Mechatronics LLC from US for different type of unipolar and bipolar step motor angle, and with the step angle of 7.5 degree, then step accuracy of plus minus 0.5% out of and different specification of this motor. Then it is essential to low cost, low torque, low speed machines ideally suited for application in the field such as computer graphical, office automation, valve and fluid metering and instrument, as in the different photograph you can see its application. Now the typically operation of hybrid stepper motor, as long as the stator winding A and B are energized in a particular manner, the rotor stage put into corresponding position, and rotor will move further only when pattern of the energization of stator winding is changed, and figure A to H in the next slide present the program sequence, and A then the single phase excitation of the two phase excitation. So you can have a single phase excitation at a time or two phase excitation, and these figure 8 steps in which the rotor 45 degree, and here is a one of the two phases are alternately also energized. Therefore, sequence is not hybrid or mix in the two. So you can just see clearly, the excitation of one phase or excitation of two phase or alternate excitation, typically of one phase then two phase and then one phase. So all these, really you can look into how the excitation, how the position and how the field position is there like typical. So typically here you can see with the how different parts is clearly visible that how flux path is there. So you can see in magnet it is a parallel to the shaft, we call axial flux movement, and but in the rotor teeth as well as in stator teeth we have flux moving that is radially, and on stator coat also it's have a typically the axially. So it carries a cylindrical permanganate sandwich between the two rotor discs, and the stator and rotor both are made of soft iron stamping, and each rotor disc has 50 teeth, and the stator has a 8 pole and the 5 teeth on each. So that makes the 40 teeth on the rotor. There are 40 poles on the stator which can be perfect alignment or misalignment depending upon the switching of the typically the winding. Now for this permanent hybrid stepper motor, theta is 360 divide NR into kWs. So this is 60 by Z, and where NR is the number of teeth on the rotor disc. So kWs is here 4 step sequence, either single phase or two phase on, and 8 for step, whether typically 1 and 2 or hybrid sequence of energization of stator winding. So here you can see a large number of teeth on the stator and rotor give a smallest basic step size, and the stator has a two phase winding, and each phase winding consists of two sections. And here in a hybrid stepper motor, which is we told popular with a 1.8 degree performing 200 steps per revolution, and cross section only in the winding of a phase is shown here in the left side, and typically the permanent rotor edge is shown how it is really the magnets are typically placed parallel to the shaft like. So you have stator core, then the permanent ferromagnetic disc, and then the shaft like. And here it is the typical photograph of all these parts. As you can see, two phase hybrid stepper used for moving the print head assembly on inkjet printer. So you can see stator is bound with the coil, with the you can see with the cylinder pole structure, and the rotor is two stacks are misaligned by half the step, you can call it angle, and shaft magnet are put parallel to the shaft in that case. So now coming to the characteristic of stepper motors. Here you can see the stepper motor characteristic, torque versus speed characteristic. You will find typically with respect to the rated torque, how really the torque varies with the speed. In case of, you can call it ideal or practical motors, and it depends on the voltage also, how the torque is on how the voltage and the full voltage like. So torque varies inversely with the speed, and because the current reduces as the speed increases, and we are not able to push that much current for given voltage. So current is proportional to torque, and torque is, it means current should be infinity, which leads to motor damage. So torque thus needs to be limited with the rated value of the motor. So here you can see torque angle characteristic, which you call it static characteristic of this and then the linear portion in which we normally operate the motor with the torque and current characteristic. Then hybrid stepper motor torque, which have a really motor torque with respect to the step angular, but it has a, you can call it deterrent torque due to the permanganate excitation, due to presence of permanganate, which really try to have a given a deterrent torque according to the number of magnets and the position like. Now in these characteristics we have a pull-in, a torque speed characteristic here, and we have a start stop mode and slewing mode. So here pull-in, we have a pull-in curve correspond to start stop of a single stepping mode, and pull out is the corresponding to the slew rate. So as you can see here in the figure, we have a response range, we have a slew range, and we have a pull out range and pull in range in the characteristic like. So now coming to, of course, we have a start stop, rotor comes from rest to after one step, and slew mode rotates. Rotor still rotates in response to previous pulses when next pulse arrives. Therefore, motor can overrun by several steps before stopping. And mid-frequency resonance, as you can see in torque characteristic, at half the speed there is a resonance, which really give a dip in the torque. Either you excite one winding or two winding, it is present in both cases. So the pull-in curve of the stepper motor suddenly dips very low in particular range of stepping motor, and this phenomena known as manifestation of instability of the motor operation. Now, typically you can see speed characteristic of that various phase current, the various phase current here. I mean, typically how steady characteristic with the step angle or step position. Manufacturers generally supply information about the torque producing capability of the stepping motor and the torque developed by the motor as a function of rotor position of several values of winding current. Now, this steady characteristic, if the appropriate sets of rotor and stator teeth are completely aligned, the no torque is produced by the motor. And if the rotor is slightly displaced from the step position to force is developed between the stator and rotor, as you can see here. I mean, like, so you get a zero torque when they are aligned. I mean, typically like alternating current. So, defining the step angle, it is the angle through which the unloaded stepper motor rotates for every step of energization sequence, that is theta equal to 360 by Z, where steps per revolution Z for heavy stepper motor Z is equal to NR into kWs, where kWs for 4 is sequence, that is 1 phase or 2 phases on, and kWs is 8 step, that is 1 and 2 or hybrid sequence of energization of stator winding. So for single stack variable luminous motor, NS equal to NR plus minus P, where P is the number of teeth per phase, minimum 2, and Z equal to PM in bracket M minus 1 for NS greater than NR, and P into M plus 1 for NR less than typically NR, where NS and R are the number of teeth on rotor and stator assembly, and M is the number of phases, minimum 2 with 3 in case of variable luminous motor. Now coming to holding torque, it is the maximum load torque which the energized step motor can withstand without slipping from the equilibrium position. And we have a detent torque, it is the maximum load torque with which the energized stepper motor can withstand without slipping, and detent torque is due to the residual magnetism and therefore present in permanganate and hybrid stepper motor. And torque constant, it is the initial slope of the torque curve of the stepper motor and also known as a torque sensitivity. And then pull-in torque, so it is the maximum torque that stepper motor can develop in the start and stop mode at a given stepping rate Fs, the step per second, without losing synchronism. Now the pull-out torque TPO, it is the maximum torque that the stepper motor can develop at a given stepping rate Fs in the slowing rate without losing synchronism. And pull-in rate, it is the maximum stepping rate at which the stepper motor will start and stop without losing synchronism against a given load torque T. Pull-out rate FPO, it is the maximum stepping rate at which the stepper motor will slow without missing steps against a load torque T. The response range, it is the range of stepping rate at which the stepper motor can start or stop without losing synchronism at a given torque T, and response spans step rate Fs less than FPI. Slew range, it is the range of stepping rate FPI where your Fs will be less than FPO and greater than Fi, at which the stepper motor can run in a slowing mode against a given load torque T without losing synchronism. And synchronism, this term means strict one-to-one correspondence between the number of pulses applied to the stepper motor and the number of steps through which the motor has actually moved. And stiffness, it is the slope of the state torque rotor position characteristic at equilibrium position. Now coming to the converter topology for stepper motor drive. So here 3-phase unipolar drive circuit is there with of course the base drive of the transistor BJT, and of course it is preferred because you have a common ground, so the base drive need not to be isolated, so it become very cost effective, like also. So we put the resistance in prevailing path as well as put a forcing resistance also, because the voltage are normally made a standard voltage, but you want to really control the current in the motor winding, to really avoid the many of the phenomena like typically overrun or overstepping. For that you can adjust the current depending upon the application requirement and torque desired by the motor, because we make the motor of a series of the motor as well as for a particular voltage, but you have to adjust the torque and current corresponding with this. That's the reason these couple of resistance are required in this motor. Then the bipolar drive circuit of one phase, this is H-bridge, but of course it requires isolated base drive for all the 4 transistors, but the major benefit, you can have a bidirectional current, and this kind of the you can use, of course, for well electronics motor, but we don't prefer use this because there we can use typically of single device as we have shown earlier. But this is normally required for PME stepping motor as well as the hybrid stepping motor, where you have to change the direction of current in the winding. So I mean, because of the polarity of the poles from the rotor side is already because of palm magnet, and you have to create the accordingly that the magnet alternating magnet from the stator side also. So you require bidirectional current in the this diverse circuit winding. For that it is used. Of course, there is another method we call unipolar circuit for one phase of bipolar one. So here we use the two winding in parallel in the two sections, and we connect in this manner. I mean, the two transistor we use with the opposite polarity of the half the winding, and here of course the advantage is that still the base drive is common and cost effective. I mean, here including you really require a different polarity of the poles from the rotor side. So you can energize one side one polarity, another side another polarity of the your electromagnet which is developed from the excitation of stator winding, and then the resistance are put for again for the limiting the current for given specified supply voltage and for the motor rating, winding rating. There is another unipolar drive for one phase excitation circuit. I mean, like you can just see here that you can excite the whole voltage by exciting there, and but after that you can typically I mean take the energy out from the winding by using the kind of field length action by when you really switch off the both the transistor, and as of course how it is really the characteristic of the motor with rise of current and maintain current. And then similarly for with the hysteresis control, how really for this construction current limit control you can put it with the on off, and how the applied voltage, how the gate drive for this transistor typically produced in this single phase excitation or unipolar excitation. Now coming to control scheme for stepper motor drive. Now microprocessor based open loop control basically for stepper motor is used with, you can use the microprocessor for giving a program sequence of the pulses for particular application. I mean, there we need the processor virtually here, which gives the signal to the through IO to driver circuit, and then you have a typically the going to be from driver circuit the phase current to the motor, and then the connected load on the shaft of the motor. So you can easily control this motor with the help of processor for changing the programming sequence or different, because you can put the different software for the control in microprocessor. Now coming to constant stepping rate for open loop control. So normally we have here start and stop virtual sequence, and we have a constant frequency clock. Then we go to excitation sequence generator, which really converted the pulses for different transistor of different phases. Then you have a converter give the phase current to the motor, and then it goes to the motor develop the torque to drive the load. So that is virtually how really the operation of this control is there, like I mean for. And then for closed loop, in closed loop of course we take a position. You are not normally preferred because of the cost constraint and the reliability issue, but of course in many cases we consider the position sensor to back, and we start with this control unit. Of course we give a count as a load also here, and then we have a step commands with the retard, and then phase sequence generator give the typically the gating pulses for the driver circuit, which really produces the current in the winding when winding is connected to this driver circuit. And of course the position sensor really gone back as a sequence like. Now coming to concept of micro stepping control of stepper motor. I mean typically, so in even including the it can be used in hybrid stepping motor, a micro stepping, energizing both phases with equal currents produces an intermediate step position half the way between the one phase on position, and if the two phase currents are unequal, the rotor position will be shifted towards the stronger pole, and this effect is utilized in the micro stepping drive, which subdivides the basic motor step by proportioning the current in the two winding, and in this way the step size is reduced and the low speed smoothness is dramatically improved like. And you can just see how it is a micro stepping really characteristic is there with the stepper. So micro stepping control enables the stepper motor to move through a teeny micro step of its step size delta theta much smaller than step angle theta s in response to input pulses, and this overcomes the limited resolution and mid frequency response problem, and the pull out characteristic of micro stepping control is shown here. So in micro stepping control, the stator magnetic field is made to rotate through a small angle theta much smaller than your theta s, that 90 in response to input pulse, and this is achieved by modulating current through winding B2 and A1 in such a way that IB2 equal to IR cos theta and IA1 equal to IR sin theta, and the resulting magnetic field will be at the angle of theta with respect to the positive real axis, and the phasor diagram and the sequence table for the microstepping are given in the next slide. The torque developed is the same as developed under the one phase on sequence, and resulting current typically remains IR. You can just see how really microstepping works. Here with the torque, like you are putting a current IR sin theta, IR cos theta, and resultant field is go to typically at the angle of theta. So you can say here, if the torque required by under two phase excitation sequence, then the magnitude of current should be such a way that IA2 plus IB2 equal to 2. And here for the microstepping, we have a typically the circuit here with the which we have a current control, and then we have a diverter, the switch S1 S2, that which portion of the winding of the A phase and which phase part of the winding of B phase is there, whether A1 or A2 or B1 or B2, we put the current in a typically little in kind of vector control mode like. So you can just see here how really motor winding are excited in counterclockwise direction and your clockwise direction with the single quadrant or quadrant as per the standard convention with the sine and cosine excitation for different phases like also for micro. And this is a way of implementing how people have implemented even using microprocessor 8085 with the other peripheral to develop this with the digital to analog converter, the kind of the waveform with the sine and cosine waveform with the demultiplex. It goes to the power driver circuit of the your device is typically of the 4 segment of the 4 transistor connected for 2 phase with the midpoint converter like. And this is the block diagram of micro friend kit with the 8085 microprocessor, how it is really different parts are connected to it. Now coming to high resolution microstep drive, the high resolution microstep drive divide the full step into a many edge 500 microsteps, giving your 100,000 steps per revolution. In this situation, the current pattern, the winding closely resembles to two sine wave with a 90-degree phase shift between them, and the motor is now being driven by very much through its conventional AC two-phase synchronous motor. And in fact, the stepping motor can be driven in this wave from a 50 Hz or 60 Hz sine wave source by including a capacitance edge with the one of the phases. So coming to advantage of micro stepping, the improvement in resolution by a factor of MSR, microstepping rate, that is MSR equal to theta s upon delta theta, in as much as the smallest angle through which the motor rotates toward a unit impulse pulse. So delta theta is 1 upon MSR, and theta usually values of MSR are 5, 10, 125 and up to the power of 2 up to 128, and the rapid motion at microstepping equal to MSR into Fs, where Fs is the full stepping rate, and DC motor like a smooth performance and elimination of mid-frequency resonance. Now coming to the theoretical problems. Question 1. What is the fundamental principle behind the operation of a stepper motor? A stepper motor operates on the principle of conventional electrical pulses in discrete mechanical movement known as steps, and it has a multiple coils and rotor with teeth. By energizing the coils in a specific sequence, the rotor advances in steps, resulting in precise and controlled rotational motion. Question 2. Explain the difference between the bipolar and unipolar stepper motor. So solution is bipolar stepper motor have 2 coils per phase, phases, and require a reversing of current flow to generate each step, and unipolar stepper motor, on the other hand, have multiple center tape coils, simplifying control by allowing the use of only one polarity of current, and unipolar motor are easier to drive, while bipolar motor generally offer better performance. Now question 3, what is the holding torque in context of a stepper motor and why it is important? The holding torque is the torque a stepper motor can generate to maintain in its position when stationary, and it's crucial to prevent the motor from losing its steps and maintaining stability in application where the motor needs to hold a fixed position. Then what is micro stepping in a stepper motor? The micro stepping is a technique that subdivides each full step into stepper motor into a smaller increment, providing smoother motion, increased precision and reduced vibration. Now question 5, describe the concept of step per revolution in stepper motor specification. The steps per revolution indicate the number of steps in a motor must take complete one full rotation. It is a crucial specification defining the motor resolution and accuracy. The common stepper motor have a step angle of 1.8 degree, resulting in 200 steps per revolution. So what are the key factors to consider when selecting a stepper motor for a specific application? The factor to be considered include torque requirement, speed, power supply, voltage, step revolution, physical size, and the operating environment, and matching the motor specification with the application demands ensures optimal performance. How does the resonance affect the stepper motor performance, and what are the measures can be taken to mitigate it? The resonance can lead to missed steps and vibration, impacting performance. And to mitigate resonance, techniques like micro-stepping, damping, and selecting an appropriate drive voltage can be employed. Question 8. Discuss the advantage and limitations of stepper motor in comparison to the other type of electric motor. The advantage include the precise positioning, simplicity of control, and the holding torque. Limitations involve lower efficiency at high speed, potential for resonance issues, and the power consumption when stationary. And stepper motor are suitable for applications requiring precise control and moderate speed. Now coming to numerical problems. Question 1. A hybrid VR stepper motor have 8 main step pole which have been cast listed to have a 5 teeth, and if rotor have a 50 teeth, calculate the step angle, where ns equal to 18 into 5, that is 40, and r equal to 50, and calculating beta, that is 50 minus 40 into 360 by 15, that comes 1.8 degree. Now question 2. A stepper motor has a step angle of 2.5 degree. Determine the resolution, number of steps required to shaft to make the 25 revolution, and the shaft speed if stepping frequency 3600 rpps. So resolution 60 by beta is given in step angle, so there's 144 steps per revolution. Now steps per revolution 44, hence the steps required for making 25 revolution is 144 into 25, that is 3600, and shaft speed and b into f upon 360, putting value it comes 25 rps. Now a single stack 3-phase VR step motor angle have a 15 degree. Find the number of the its rotor and stator pole. So beta equal to 360 by m nr, or 15 degree equal to 360 by 3 into nr, and nr is given 8 here. So for finding out the value of ns, we'll use the relation beta equal to ns minus nr, 360 divided by ns nr. When ns is greater than nr and beta is 15 degree, so we get the ns equal to 12, putting the value into it. When ns is less than nr, putting the value of beta into it, it comes ns equal to 6 like. Now coming to question 4. A 4-stack VR stepper motor has a step angle of 1.8 degree. Find the number of its rotor and stator teeth. Here the 4-stack has a 4 pole, hence the m equal to 4. So 1.8 degree equal to 360 by 4 into nr. So nr comes 50. And since in multi-stack motor, rotor teeth equal to the stator teeth, hence the ns is also 50. Coming to question 5. A single stack 8-phase multiple pole stepper motor has a 8 stator teeth. Calculate the A step size, B steps per revolution, C step speed in RPM. Excitation frequency is 80 Hz. So beta solution is beta equal to 360 by m nr. Putting the value 360 by 8 into 8, it comes 5.625 degree. And step per revolution z equal to 360 divided by the step angle 3.6. This comes 64, and speed in RPM and equal to frequency upon number of rotor poles, f into nr. So that comes 80 upon 8. That is 10 RPS or 600 RPM. Now coming to question 6. A 2-pole permanent stepper motor have 12 steps per revolution. Calculate the number of step phases and the sequence. The number of stator phases, m equal to z upon nr equal to 12 upon 2, that is 6, and sequence excitation and sequence winding of the rotation of 12 step is given here in A, B, C, D, E, F, and excitation sequence you can call it A, B, C, D, F. In phases are assumed to be A, B, C, D, E, F. Now coming to question 7. In a single stack variable reluctance stepper motor, a step angle of 7.5 degrees required. Calculate 2 types of stepper motor in terms of number of phases, number of steps per revolution, number of stator teeth and per phase, and number of rotor teeth. So here beta equal to 7.5 degree. Let the m be the number of phases, nr is the number of rotor teeth, ns is the number of stator teeth, z is the number of steps per revolution. So z equal to 360 by beta, that is 360 by 7.5 degree, 48, and r equal to z upon m. So now coming to solution 1, taking m equal to 3 and r equal to z upon m, so 48 by 3 16. So when nr is less than ns, so ns equal to z upon m minus 1, that is putting value 48 divided by 3 minus 1, 24. When number of stator teeth ns divided by m is 24 by 8 when n are greater than n, that is ns equal to z upon m plus 1, or 48 divided by 3 plus 1, 12. The number of stair and root, number of stair teeth per phase, that is ns upon m equal to 12 by 3, that is 4. Now solution 2, taking m equal to 4 and r equal to z upon m, the 48 by 4, that is 12. When nr equal to ns less than ns, ns equal to z upon m minus 1, so that becomes putting value 48 by 4 minus 1, 48, so 16. And number of stair teeth per page, that is ns upon m, that is 16 by 4 is equal to 4. When nr is greater than ns, so z equal to z, ns equal to z divided by m plus 1 equal to 48 divided by 4 plus 1, that is 9.6. This is not valid design. Now coming to question 8, consider the 3-phase 6 by 4 variable reluctance motor. The stator phase are excited sequentially, equating a total time of 15 seconds. Find the angular velocity of the rotor in RPM. So here the rotor will rotate 15 degree at each consecutive phase is excited. Thus the rotor will rotate at 1 revolution in 8 into 15, that is 120 milliseconds. Thus it will rotate at 1 divided by 0.12, 8.33 RPS or 500 RPM. Coming to question 9, a single step 4-phase multiple pole stepper motor is needed to provide 15 degree step motion. Calculate the number of rotor poles and stator poles. Hence, z equal to 360 divided by step angle, that is 15 degree, equal to 24, and r equal to z upon m, that is 24 by 4, that is 6, and z equal to 1 upon ns, nr minus 1 upon ns absolute, or equal to ns nr divided by ns1. So putting value here, 24 for z, and then nr equal to 6, so it comes ns equal to 8. Now coming to question 10, in a hybrid stepper motor, step angle of 1.8 degree is required. Calculate the design data for this hybrid stepper motor in terms of number of phases, number of step per revolution, number of stator teeth per phase, and number of rotor teeth. Here, assuming the number of phases equal to m equal to 4, and steps per revolution z equal to 360 by beta, or 360 by divided by 1 by 200 steps, and number of rotor teeth nr equal to z upon m, that is 200 by 4, that is 50. To find the number of stator teeth, ns equal to the following equation used: z equal to ns into nr, ns minus nr, nr minus ns absolute. So putting the value, it comes ns equal to 40, and teeth per phase p equal to ns upon m, that is 40 by 4, that is 10. Coming to question 11, consider the multi-stack multi-phase well advanced stepping motor with 14 poles on each of the rotor and stator stacks and 3 stacks with 1 phase winding per stack. The motor is built such that the stator poles of each stack are aligned. Calculate the angular displacement between the stacks and determine the frequency of phase current to achieve the speed of 900 RPM. So here part A, the displacement angle will be 360 by 3 into 14, that's 8.7571 degree. In part B, there will be 1 revolution of the motor for every 14 cycle of the phase current. Hence the F equal to 900 by minute, and putting 1 minute by 60 into 14 by R, that's a 210 hertz. And these are the references and textbook from which the material is produced. And thank you.